Wat. Hello! It's been a while since I've had a chance to record. I was on vacation and then I got sick, and now I'm just recovered enough to make a video. Today we have a request from a subscriber. Thank you, Eldon, for setting this one in. This one is based on a Stack Overflow question asking for an implementation of a lambda which raises an exception. I'm going to show you the answer and then describe what the heck is going on. Let's jump into it. So the first solution is perhaps the easiest to explain. The first solution defines a lambda, which contains a parenthesized generator, which calls the throw method on that generator. When called, that raises the exception. You can see in the stack trace that we get a stack frame for both the lambda and the generator. Generators are pretty cool, and they're a kind of advanced topic in Python. I'll probably explain them in another video, but here's the TLDR. Generators allow you to implement coroutines, that is, code that can be run asynchronously and concurrently. And generators have three operations: next, send, and throw. The answer on the previous slide abuses the throw operation. The next solution is the totally WAT one. Like, what is even going on here? Fortunately, I'm here to explain that. But as you can see here, it looks like a lambda and raises an exception. I've taken the snippet from the answer and modified it a bit so that we can assign it and call it. You'll see that whatever exception object is passed into the lambda ends up getting raised. So let's break it down. The first thing we'll look at is type of lambda 0. This is just a way to retrieve the type of a function object. And in fact, this is the same way that lambda type is defined in the standard lib types module. PyDuck can help us figure out what function type actually is. We can see from the argument signature that it takes several arguments, and we'll be using the code and globals argument. The next thing we'll look at is type of lambda0.funcCode. This is a nifty way to retrieve the type of the function's code object. It is in fact the same as types.codeType. I'm using Python 3 and the answer was given for Python 2, so the standard lib definition of codeType uses double undercode instead of funcCode. And in fact, if you're using Python 2.7, you can also use double undercode. If we look at code type using PyDuck, we'll see that it takes a ton of arguments. I won't really explain all of these since there's kind of a lot, and we really only care about a few of them. So if I take our original answer and substitute in the two things we figured out so far, the answer seems a little less surprising. We're basically just constructing a function object and a code object. So now that the expression makes a little more sense, let's look at what sort of function object we actually created. The first thing to look at is the arguments that the function takes. One way that we can figure this out is by using the inspect module. Inspect contains a lot of procedures for doing reflection. In this case, we can use getArgSpec, or if you're in Python 3, getFullArgSpec. Using this, it tells us that our function object takes a single positional argument named x. The other thing that we'll do to look at this function is use the dis module. Dis is a disassembler of Python bytecode into readable chunks. It's often useful to figure out what is going on in code golf solutions. Python implements a stack virtual machine. That is, source code is compiled into opcodes, and each opcode either pushes, pops, or performs some sort of side effect. When we disassemble our function object, we can see what is actually going on. In this case, it's two opcodes, the first being load fast, which loads the variable at position 0, in this case our named parameter x. Load fast takes the loaded variable and pushes it onto the stack. The second opcode is raise var args with the operand 1. In this case, it means pop one argument from the stack, the exception object, and raise it. If I were to make my own function which does the same thing, we'll see that the disassembly is basically the same. One notable difference is ours includes the implicit and unreachable return none at the end of the function. The answer on Stack Overflow cleverly optimized this bit out. I've also taken the liberty of porting this answer to Python 3. The solution is basically the same, but the Python 3 code object grew some new parameters. I also implemented a solution which doesn't take any parameters at all. Here's the disassembly so you can see what is going on. That's all I have for this video. Thanks again, and have a WAT one!